the north, winter in the south. 6 months later, it is just the opposite. It is now summer in the south, winter in the north, because of the tilt. Now you can ask me, okay, I understand, because of the tilt, season changes occur. But why do you have to tell it in a big way? Do you know if there were no change of seasons, what would have happened? If there were no change of seasons, there would have been no ocean currents. And if there are no ocean currents, there would have been no air currents in our atmosphere. And if there are no air currents in our atmosphere, clouds would not have born somewhere and gathered somewhere else and gave us rain and fresh water. Life would not have been possible because just after Earth was born, it would have been a barren desert. So you and me exist now. It is because of this accidental tilt of 23.5 degrees. A solar eclipse, one of the spectacular events in nature. And you all know why it happens. One side is the sun, middle is the moon, one side is the earth, sun's rays falling onto the moon, moon's shadow falling onto a small patch of space, and people staying on that patch of space at that particular moment will see as if the sun has vanished, right? This is a beautiful picture taken from the International Space Station, how you can see the sun has been eclipsed and a shadowed region over the globe of the earth. This is a very beautiful picture. As the earth is spinning around its axis, see how the shadow of the moon crosses the globe of the earth. Basically, this gives you the path of total solar eclipse. At the highest point, it can be around 950 kilometers or so. It was during an eclipse, sun was discovered as a new avatar. Scientists found out from the surface of the sun, milky white radiation is coming out, which cannot be seen on other times. When they asked themselves the question, what is causing this? They were amazed with the answer. They found out from the surface of the sun, every second, 1.6 million tons of charged particles on an average are coming out. These charged particles, as they move through the magnetic field of the sun, they produce this milky white radiation. The average velocity of these charged particles are 450 kilometers per second. With that speed, they have enough momentum, enough energy. If they hit any atom or molecule, it will instantaneously break apart. So basically that means tomorrow when the sun comes up, if I go and stand on the sun, the charged particle coming from the sun's surface, the moment they hit my body, within fraction of a second, my whole body should disintegrate, but I'm alive. How I will come to that? Tides, a very important phenomenon, my friend, because you have all learned in our childhood, life first occurred on the oceans. How did it come onto the land? Suddenly it grew legs? No. Every day, high tides used to bring ashore multicellular organisms, and water used to go down, they used to get stranded and get killed. But over millions of years, they got the adaptation of staying alive. And from there, different animals, different organisms, different reptiles occurred. Monkeys arrived, and from monkeys, we have arrived. So that we are here are because tides are there. Now, if I ask you, why does tide occur? I think everybody gives a bang answer. It is the moon which is gravitationally attracting the water on the earth, causing the tide. But my friend, those of you who have done Newton's laws of universal gravitation, you all know Gm on m2 by r square. If you do a back of the envelope calculation today, you can show sun is attracting Earth 173 times more than the moon does. Then why do you say it is moon which is attracting and causing the tide? Because, my friends, tide is not a force. It is rather the resultant of quite a number of force over unit distance, right? And that is the reason it's a force derivative, technically m1 m2 by r cube. And that is the reason, since moon is 384,000 kilometers away and sun is 15 crore kilometers away, moon wins. But a lot of our teachers have failed to tell us sun also attracts the water on the earth, sometimes 47% than the moon does. It's not a small amount, right? Now, suppose I'm sitting here and the sun and then the moon is just in front of me. Because of the moon's presence, water bulges in this direction and I see a high tide. So only after 24 hours, I'll come back in the same position. By that time, moon may have shifted a little bit. So roughly after 24 hours, I should have another high tide. Then why do we get two high tides a day? It is because when I'm facing the moon and I'm having the experience in the high tide, just opposite, 180 degrees away on the other side of the globe, because of the interplay of the inertia of water and the gravitational force, or the centrifugal force and the gravitational force, water bulges in the other direction also. And that is the reason we get two high tides a day. Once when I'm facing the moon, once when I'm 180 degrees away from the moon. Beautiful picture taken of the moon. You see the earth arising from the horizon. What is moon? According to 98, 99% of the scientists, 4.51 billion years back, a huge piece of rock came and slammed into the earth. With such a force, huge amount of the surface material got gouged up and was thrown up into space. It couldn't go away forever because of the Earth's gravity, but going to a very vast distance over millions of years, it condensed, coalesced, coagulated, and ultimately given birth to our moon. This theory goes by the name the collision ejection theory, or sometimes it is called the giant impact hypothesis. Though there are three other theories, co-creation theory, capture theory, and fission theory, but 99% of the scientists believe in this theory because of a lot of proofs that one has found in the lunar regolith, that is the surface material which has been rocks that has been brought back from the moon onto the earth. It is now our time to start our journey in space and time as well. Why time? The journey must be in space. Because, my friend, you all know, 1905, Albert Einstein gave his theory of relativity, the special one. And one of the outcomes was that light travels at a constant speed in a particular medium. And the velocity of light is 3 lakh kilometers per second in vacuum. The distance from sun to earth is 15 crore. 3 lakh kilometers per second is the velocity. If you do a simple division, any class 7, 8 book, geography book, amazingly, gives you the information that light takes 8.3 minutes to come from sun to earth, or the light travel time from sun to earth is 8.3 minutes. But basically, what does it mean? It means when tomorrow the sun comes up, look at the sun for a fraction of a second and tell yourself, the sun I saw now, this is the image of the sun as it was 8.3 minutes back, and I'm seeing it now. The closest star, Proxima Centauri, 4.2 light years away. Today evening, if the sky is clear with a binocular, look at the star and tell yourself, the star I'm seeing now, it is the image of the star as it was 4.2 years back, and I'm seeing it now. So next time, if you're visiting any metro cities and the younger ones in your family tells you to take to the science city, spend 50 rupees on a time machine ride, never. Go out into the open in a clear night, tilt your head. The deeper you are seeing your own past. We don't understand that the moment you look up in the sky, it is not a journey in space, but the journey in time. Our first stoppage of the journey will be the solar system. These are all more or less the true color pictures of the main avatars of the solar system: Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Poor Pluto has been kicked out. Sun is a ball of gas. But you tell me, my friend, if you take a football, pump in a lot of colored gas, cut open the football, will the gas inside remain like a ball? It will diffuse out. Then how come Sun, being a ball of gas, is not diffusing out into the sky? What does the scientist say? According to the scientist, 460 crore years back, or 4.6 billion years back, a huge cloud of gas and dust was floating in space. This cloud was made up of, in terms of number of particles, 91% hydrogen, 8% helium, 1% rest other element. In terms of mass, 74% hydrogen, 25% helium, 1% rest other elements. The average temperature of this gas cloud was minus 240 degrees centigrade. At this very cold temperature, out of the 4 fundamental forces of nature, only one type of force becomes dominant, the force of self-gravity. The force of self-gravity will attract the periphery of this gas cloud towards the center. As the gas goes toward the central density rises. As the density builds up, pressure builds up, temperature rises. And starting from minus 240 degrees centigrade, the temperature rose to a fascinating level of 1.5 crore degrees centigrade, which is enough to fuse 4 hydrogen nuclei or 4 protons. As if they come together, they don't come together 4 of them, but as if 4 hydrogen nuclei fusing to give rise to a helium nucleus. This thermonuclear fusion reaction produces huge amount of energy. As the energy, as it is produced, it tries to come out. It produces a back pressure or a radiation pressure. Sorry. This radiation pressure, when it exactly balances and matches the inward force of gravity, Sun, being a ball of gas, remains hanging there for millions of years. And it's an amazing natural phenomena. Starting from the center to the surface, at every gas layer, these two forces cancel out each other. This is called the conditions of hydrostatic equilibrium. How did the solar system happen? It was a huge gas cloud with a spin. So as it was spinning and becoming smaller, it never became a smaller solid, spherical object. Why? Because of the spin. Because of the conservation of angular momentum, a spherical object, as it is spinning and becoming smaller, it will condense into a disk. At the central part of the disk, where the temperature rose to 1.5 crores, sun was born, and in the outer periphery, where the temperature was less, gas and dust collided, condensed, coagulated, and has given birth to our planetary system. If I bring down the sun from the sky, cut it open like a watermelon, inside there are three regions. The core at the very center where the nuclear reaction is going on, then the energy that is produced for over a huge volume, it freely flows for the radiative zone, and then sun is very nice, funny looking object, my friend. 650 to 700 kilometers deep, pillars of gas, columns of gas stacked one after another. Heat comes from inside, hits the bottom layer of the gas pillar. Gas, when it is heated, rises up, comes to the surface, deposits the heat as sunlight, becoming cold like a fountain, again goes down and raises the heat continuously from inside. This is called the convective zone. Outwardly, sun is again divided into three regions. The sun that you get to see in the early morning or evening, photosphere, sphere of light. Over the photosphere, in a very thin layer, exquisitely pink-colored gas can be seen, and that is called the chromosphere. Chroma means color. And for thousands and thousands of kilometers, milky white radiation called corona. Nothing to do with this coronavirus. Corona in Latin means crown, as if sun is wearing a crown. Do you want to see how sun really looks? See this on the upper left, right? In your case, maybe upper right, whatever. It is this sort of a very scratchy mottled surface. If you really look closely, it has this beehive-like structure. Each cell is a column of gas. As the heat is coming through the middle of the gas column, it is lighted. The moment it comes on the surface, deposits the heat as sunlight, becoming cold and going down. Since the heat is lacking, it is typically dark in color. The average size of each of these cells is 950 to 1,000 kilometers in diameter. And in the lower left, you can see chromosphere. Spikes of gas coming out from the surface called spicules. Later on, scientists have proven that these spikes, they transport the magnetic energy from the surface of the sun and deposits the energy thousands of kilometers away from the surface, thereby raising the temperature there millions and millions degrees centigrade. Though the surface temperature of sun is around only 5,600 degrees centigrade. And it is one of the most beautiful pictures that can happen. Solar corona, milky white radiation coming out. You may ask that, how do I know about the inside of the sun? Has anybody visited? No, it's too hot. It is basically, these are all model calculations. You put in all the information that you have inside a computer. Take help of very four simple differential equations of mass conservation, hydrostatic equilibrium, energy transport, and energy generation. And then crunch, crunch, crunch comes out the model of the numbers. Sun sometimes becomes very active. You get to see black splotches on the surface of the sun. Sometimes one, sometimes 10, 20 in a group. They are called sunspots. What are they? At the surface temperature of 5,600 degrees centigrade, gas cannot remain as gas. It becomes plasma. Plasma has a property. Wherever there is a magnetic field, plasma will try to get deflected from it. On the surface of the sun, very randomly small pockets of magnetism to form. A column of plasma trying to bring the heat from inside, if it realizes that there is a magnetic field above it, it will not come out straight. It will take the heat away from different directions. No heat comes out from those regions, and they look dark and are called sunspots. This beautiful picture taken in 2012 by Solar Dynamical Observatory, a NASA mission, tells us that sun is not a smooth object as it appears to our skies in the early morning or late evening. Tremendous amount of explosions are happening every second on the surface of the sun. Thousands of tons of gas are getting thrown out from the surface, reaching a height of 25,000 kilometers, making beautiful arch and loops, falling back onto the surface. Sometimes they get thrown up with such a force, they get detached from the surface of the sun and flow past the whole solar system like a solar wind or solar storm. Beautiful picture, right? Taken in 2015. You see, amazing picture. Thousands of tons of gas are getting thrown up and making a beautiful loop falling back. Do you know what is the size? The cavity you can see inside that loop, 3 Earth can go side by side inside that cavity. Amazing. I told you that this charged particle coming out of the surface of the sun with the velocity and the momentum, if they hit anything, they will destroy any atom or molecule. Why we are alive? Again, you come to know, like this 23.5 degree tilt, like the formation of the moon, there is another chance happening which has created life on Earth. Earth behaves like a bar magnet. Around the Earth, like a peels of an orange, there is an invisible magnetic shield. These charged particles, they come and slam onto the magnetic shield, cannot enter, flow past the Earth, and we think we are the king and queen of ourselves. But if you remember your class 8 days, drawing the magnetic lines of force of a bar magnet along the north and magnetic polar region, there are open field lines. These charged particles, they get reconnected through these open field lines, enter the Earth's atmosphere. Before hitting the ground, they interact with the air molecules and let them glow. And what do you get to see? Auroras. Aurora borealis in northern hemisphere, aurora australis in southern hemisphere. This is an amazing phenomena, beautiful picture. Nowadays, internet is abuzz with this, and I have, in my personal thing, I have taken one or two. But the point is that it also tells us that how every second sun is interacting with our Earth. That is important. And that is the reason there is something called a space weather. Parker Solar Probe, you must have read about it, is going very close to the sun, trying to understand how the solar corona behaves and how it interacts with the atmosphere of Earth or any other planet. Because we have to progress, we have to get to know all these facts. Solar system, how did it happen? As I mentioned, 460 crore years back from the disk of gas and dust at the center when sun was getting born, in the outer periphery, gas and dust condensed, coagulated, gave birth to very hot spherical objects. For millions of years, they dissipated away the heat, and at least the first four, Mercury, Venus, Earth, and Mars, become terrestrial or rocky, whereas the other four, Jupiter, Saturn, Uranus, and Neptune, are mostly made up of gas. This is a collage of all true color pictures of the planet: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and poor Pluto. Venus, the second planet, covered by a thick layer of sulfuric acid, right, vapor. So when it rains in Venus, it is drops of sulfuric acid. Carbon dioxide content of the atmosphere is 96.5%. The greenhouse effect is so critical, it being the second planet is still the hottest planet of the solar system. Forget about Mother Earth, at least today evening. Next is red planet Mars. Why red? Rusting on the surface. Ferrous and ferric oxide covers the whole region. But this 2001 photograph taken by Hubble Space Telescope has interested the scientists because in the polar region, they have found white sediments. According to them, this white sediment is a mixture of mostly water ice and dry ice, that is carbon dioxide ice, with a little bit of methane ice also thrown in. According to them, even if a part of it is water ice, maybe liquid water is to flow on the surface of the Mars millions of years back. And on Earth, liquid water is synonymous with life. So was there life on Mars? Is there still life on Mars? Amazing question. Jupiter, 319 times heavier than the Earth, takes 11.86 years to go around the sun once, but takes only 9.5 to 10 hours to go around itself. With a tremendous spin, it has dragged the clouds of the atmosphere and created this belt-like structure. Saturn, one of the most beautiful planets of the solar system. Fantastic ring, takes 29.4 years to go around the sun once. Uranus with a ring, yes, they have found rings of the four outer planets, Jupiter, Saturn, Uranus, and Neptune. And Neptune, blue in color, covered by methane-bearing clouds. Methane haze is typically bluish in tinge. And then our Nandemunne Pluto, with three of its measured moon, Charon, Nix, and Hydra. Mars. By the way, I'm not using my mouse, but somebody is actually drawing it. I think some students are getting very energized. Mars. Last 20 years, every now and then we get to hear about Mars this and Mars that. Why? Because they have found these sort of geological features, as if liquid water has cut through the surface of the Mars. But there is no trace of liquid water on the surface of the Mars for the last million years, right? So when Phoenix in 2008, as it landed onto Mars and after some days scratched a little bit, they found these white sediments. Scientists were happy because after 4 days, you see in the inside 3 whitish pebbles, they were not to be seen. This is probably for the first time they have found proof of water ice outside the boundary of Earth. And then this amazing picture taken from the side wall of a crater. During summertime, you can see these black finger-like things. During winter, they are not there. Scientists found liquid water, brine, very salty, but liquid water floating on the surface of the Mars. That is the reason in 2012, when Curiosity landed onto Mars, the first set of pictures they sent us was amazing. Totally dried of riverbeds, which you get to see in the summertime if you're in Chotanagpur Plateau or some other place, arid region, right? Pebbles, which can only occur when big stones flowing through water get smashed up, broken up into small pieces, and get smoothed out by the rolling water. They have found pebbles there. So definitely, these are the signs for liquid water on the surface of Mars. And that definitely brings us to the India's mission to Mars, Mangalyaan. My friend, I'm not an ISRO scientist. I'm just a science communicator working in the planetarium. But let me tell you, I'm so proud of Mangalyaan project, because a lot of people initially, a lot of countries, they started laughing that India is not capable technologically to talk about sending a mission. But India became the first country in the whole world in its very first attempt, which successfully inserted Mangalyaan or Mars orbiter mission in an orbit around Mars on 24 September, 8:02 a.m. It was a wonderful, wonderful feeling of pride for every citizen of India, right? And the pictures it has sent us, right? My friends in NASA, they tell me these are one of the most highest resolution picture of the planet and its features by the camera which was built by the ISRO scientists. You see this from two-dimensional photographs, they are now creating three-dimensional topography. It's an amazing thing. Saturn, beautiful. Think about the ring system, thousands and thousands of kilometers wide, 80,000 kilometers actually. So if you take the Earth, you see the position of the Earth, the size of the Earth compared to the thing, right? But you'll be amazed to know this ring, this is made up of ice crystals and pebbles. How come ice crystals and pebbles are not dissipating, creating the shape and size of a ring going around the Saturn in a very regular manner is a daunting question, right? And this is, I think this takes the cake. I'm sorry for this, Marx, whoever is doing this. I think, my friend, you are spoiling all these 200 people, 210 people who are trying to see this. Please don't do it, right? You are not becoming famous, but I'm not even touching my anything. They're not my screen or nothing.
Now we understand that, and the hosts are we are unable to make out who's doing this. So we are also equally sorry for what's happening. It's one of the participants.
Right. Please.
Oh, sorry.
But this is to the participant. Professor Madhurima, you should not feel sorry, because you are all trying to help me. But this particular fellow, I know, maybe sitting on a cyber cafe, trying to show his prowess on softwares and all that funny feeling. Whatever. So now suppose you have gone to this ring system and meet an alien, and he asks, who are you? What did you answer from that distance, from Earth? You'll have to say, see, 7.8 billion of us and millions of other life forms, all the rivers, valleys, hills, mountains, everything is concentrated in that small white dot, pale blue dot, as it is called. So astronomy does a very good thing for your ego, right? From that distance, you have to say, see, you see the point? I am just a micro point in that point. Amazing, right? 1801, Italian astronomer Giuseppe Piazzi discovered a piece of rock 900 kilometers in diameter between the orbit of Mars going round Sun, named it Ceres. People thought a new planet has been discovered. Oh, but within a couple of years, three more, Pallas, Vesta, and Juno, each around 500 kilometers in diameter, were discovered in the same region going around the Sun. People realized a new class of object is getting discovered. And starting from 1801 till today, thousands and thousands and thousands pieces of rock, 10, 20, 30, 40, 50, has been discovered between the orbit of Mars and Jupiter. They called it asteroids, right? This picture is an actual presentation from NASA. Here, each green dot is a discovered asteroid, believe me, my friend. And the red dots are called Apple asteroids. Speciality, their orbit intersects the orbit of Earth. That means Earth is going around the Sun on its own. They can come, any one of them, hit the Earth at any point of time. The amount of devastation is even unimaginable. It can happen. And if you ask me, when can that happen? Really, though NASA is trying desperately to find out all of them, but it can happen any point of time. So that we are staying on Earth and alive, this is a chance happening, an accident, my friend. A lot of new studies have gone on to try to mitigate these sort of asteroid collisions with the Earth, using rockets which can be sent to the asteroid with a nuclear bomb and exploded, with something called gravity tractors, huge spacecraft going near the asteroid and trying to deflect them by their gravity from the collision course, or even putting a sail onto it so that the solar wind can impinge on them and slowly deviate them from the collision. Comets, water comets. According to the scientists, 460 crore years back, went from the disk of gas and dust our sun and solar system was getting born. At the outer periphery, where the temperature is less, gas and dust condensed, coagulated, coalesced, and has given birth to chunks of ice. Water ice, dry ice, ammonia ice, methane ice. So these chunks of ice, through soft collision, through resolution process, became bigger and bigger. And when they also started going down the sun, extremely elliptical orbit, what happened? Can you see my this thing? Hello?
Give me a second, sir. I'm sorry. We are trying to stop the annotation and something else happened. Just give me a second, please. Yeah. Can you share again?
Oh, I have to share again. Just
because the annotations were really bothering many of the participants and we were trying to clear it without disturbing you. I'm sorry for this.
Okay, just hold on a moment. I will just. So as I was telling you, 460 crore years back, when sun was getting born in the central part of the disk, in the outer periphery, temperature cold, chunks of ice, water ice, dry ice were floating around. Through soft regulation, they became bigger and started going around the sun in a very eccentric orbits. In their elliptical orbit, and as they came close to the sun, by the sun's heat, the water melted, the ice melted and created million kilometers long tail. So a comet is just a huge amount of tail, only 10 to 15 kilometers the nucleus. Are there 9 planets in the solar system? People started asking the question because in 2003, an object was discovered, 2003 UB313, in the very outermost periphery of the solar system, which takes 557 years to go around the sun once, and it's larger than Pluto. So the debate was on, and in 2006, in the 26th General Assembly of the International Astronomical Union, it was decided to change the definition of the solar system. So from then on, solar system will have 8 classical planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And a new class of objects were nomenclatured. They were called dwarf planets. Who became the dwarf planets? Pluto, my poor friend Pluto, got demoted. Ceres, the largest asteroid, and Eris, this new object, 2003 UB313, has been renamed by IAU as Eris. They were called the dwarf planets. In 2015, 2 more, Haumea and Makemake, has been incorporated into this dwarf planethood. 2006, NASA started a project called Follow the Water, tried to follow whether there is a liquid water outside the boundary of Earth. Mars is one, yes. And anywhere else, you see this. Europa, one of the big moons of Jupiter, and Enceladus. And they have found hot water geysers, hot water streaming out from the surface of Enceladus. Now they know the surface material is 10 to 15 kilometer thick water ice. Inside there is a huge reservoir of liquid warm water. As the water is putting pressure on outside, it is cracking. So 2029, we hope 2 missions, Cryobot, 2 huge drills with powerful lasers at the tip, will drill through this ice and ultimately reach the liquid water and tell us about life forms, possible life forms outside the boundary of Earth. Out of the solar system, these are all true color pictures. Amazing. You may ask, we don't see this because we cannot see, because there is something called a perception of vision. Within 1/10 of a second, whatever amount of light enters through our pupil and falls on the retina, the optic nerve immediately takes them to the back of our head to create an image. Our eyes cannot integrate like a CCD chip. If our eyes were like a CCD chip looking in a particular direction in the sky, we would have seen every dot in the sky, there is a star, and a huge gas clouds of all colors and saturations. Amazing. The question arises, oh, come on. This is so disturbing. Okay, the question arises, are the stars different from the sun? Answer is yes and no. Why yes? Because most of the stars, 91% of the stars are burning hydrogen to helium at the core. Why no? Because the stars come with initial masses, different masses, initial surface temperature, and chemical composition. In terms of mass, star can come in the range of 0.08 to 100 times the mass of sun. What is the mass of sun? 2 followed by 30 zeros, 2 into 10 to the power 30 kilograms. In terms of surface temperature, stars can come in the range of 50,000 to 1800 degrees centigrade. And it was mostly a woman, 110 years back, at Harvard-Smithsonian Astrophysical Observatory, Mary Jump Cannon. She perfected the technique of looking into the stellar images and spectra and created a classification scheme. The hottest surface temperature star, let us call it O star. Next hot is B star, A star, F star, G star, K star, and N star. Sun with a surface temperature of 5,600 degrees centigrade is just a very ordinary, very mundane G type of star. And later on, it was found out that on basis of every physical characteristic, stars can be classified into O, B, A, F, and GKM. That brings me to the life and death of stars. Stars are born from interstellar clouds of gas and dust, though we cannot see, but in the sky there are regions where one can see these clouds and also star formation processes. True color pictures, my friend. Don't think it is similar to the clouds in our atmosphere. Our atmosphere is the third planet of the solar system, and the atmosphere. From this gas cloud, 1,000 solar systems can form. See for yourself. But if you're a student of astrophysics and you are going deeper into this 2.5 million pixel picture, where each pixel is giving you some information. For example, at the top, the bluish green, oxygen 5, oxygen 6. In the middle, the blue color, it is neutral hydrogen. Yellow, sulfur. Black, iron or cobalt. Green, a little bit of zinc or molybdenum, and white on the upper left is titanium. A picture tells a story. Don't forget, astrophysics is not simple. You have to be tremendously clever. Dr. Pradhan will tell you that you have to be tremendously clever because it is only the signal of light that comes to us. You cannot bring down a star to your lab, cut it open, put chemical, test it, smell it, and say, aha, this is this. Just how difficult looking at a photograph of your friend or somebody, if you tell what is his age, what is his temperature, what is his mass, how long ago he was born, what is inside him, what is his chemical composition, can you tell it? No. But don't forget, looking at a photograph, you have to answer all these questions. Amazing technique. See for yourself. You see at the topmost, there are these 3 nodules. Each nodule, you know the size. Each nodule inside has a fully formed solar system. Universe is throwing a challenge to our human intellect. You understand, you want to understand nature. You want to go deeper, try to understand. Amazing. Pillars of creation, columns of dust, since it absorbs light, looking dark, with a tremendous force moving upward at the tip because of the ram pressure. The pressure is such, new stars are getting born regularly. Stellar nurseries. My friend, if you are born, somebody is born, you have to die. Stars also die. But stars die in different ways depending upon their masses. Stars whose initial mass is 1 to 8 times the sun's mass, then their life through the process of planetary nebula means cloud, ending into white dwarf. What is that? Take our sun, 1 to 8 times solar mass, so take our sun. How long it is going to burn hydrogen to helium? Roughly around 500 crore years, 5 billion years. When all the hydrogen at the core gets transformed into helium, the thermonuclear fusion reaction will stop. Energy production will stop. Outward pressure will stop, but gravity takes over. So it will start becoming smaller. As it is becoming smaller, the central part, the temperature will rise. In the outer periphery, slowly the temperature will rise to 1.5 crore, the temperature that was earlier at the core. At that temperature, 4 hydrogen nuclei in the outer region will fuse into a helium nucleus. Huge amount of energy will be produced. Gas, when heated up, expands. So the star, our sun, will become bigger and bigger and bigger. How big it will be? A small calculation can show you after 500 crore years later, sun will become bigger and bigger and ultimately touch the orbit of Earth. Yes, it will be called a red giant. Whereas in the central region, because of the constriction, the gravitational pressure, the temperature rises to 10 crore degrees centigrade, 100 million. At 10 crore degrees centigrade, 3 helium nuclei, they fuse together and produce a carbon nucleus. 2 helium producing a beryllium, 1 beryllium with 1 carbon produces 12, 1 beryllium with 1 helium produces 12 carbon. And a little bit of oxygen, but leave out that. When that is reached, again energy flows out, it halts. But soon, when all the helium gets transformed to carbon, what happens? Again, thermonuclear fusion reaction stops, pressure, gravitational pressure takes over. But since the initial mass of the star was 1 to 8 times, it is not enough that at that stage to produce more pressure, to increase the temperature at the core to 1,000, 10,000 million crore degrees centigrade. Because at that temperature, carbon fuses to produce other elements. So the inside will be a very hot ball of carbon in the sky, like a dot. It will be very bright. It will be called a white dwarf. Over millions of years, the white dwarf will continuously dissipate energy and start getting colder and colder. Whereas the outside, the outer envelope, will become so big, it will slowly start getting detached from the central region and will create a cloud-like structure called planetary nebula. Nothing to do with planets. But since planets were formed out of a cloud like this, at the end stage of the star, it is becoming the same, right? Over millions of years, the white dwarf will lose all its heat and ultimately become a brown dwarf or a black dwarf. And you will not be able to see it. But some scientists say you can expect a piece of diamond 10 to 15 kilometers in diameter because carbon under tremendous temperature and pressure gets transformed to diamond. These are two of the beautiful pictures of planetary nebula. And you see shells of gas coming out. And almost 20, 25 years back, 30 years back, me and my group, we did a little bit of research on that and could show through computer simulation that these shells can produce tremendous amount of shock. And this shock front with high temperature as they move fast, just below the shock, behind the shock front, because of something called adiabatic cooling, molecules can form. And it was a vibrant area called astrochemistry, synthesis of molecules in the interstellar medium. And lo and behold, my friend, this was our simulation result. Out of the 72 molecules that computer could produce, we are very lucky that within 2-3 years, in 97, Infrared Space Observatory observed 68 of these molecules in planetary nebulae. So it tells us that life is not particular to Earth. Any star in its dying state can produce the prebiotic material for life to happen. Not life, I'm saying, prebiotic material for life. Then explosive death. Stars whose initial mass is intermediate, 8 to 25 times initially. They will burn hydrogen to helium, helium to carbon. But since the mass is more, the temperature will be more at the inside. So one after another, carbon, oxygen, neon, magnesium, silicon, ultimately it will end at iron. Because iron has the highest binding energy, you cannot put two iron nuclei to fuse together, right? So the inside will take a shape of a peels of an onion, hydrogen, helium, carbon, oxygen, blah, 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 and at the core, iron ball. When that is reached, because of gravity, all these layers will start falling towards it. Poor iron fellows know how to grow. It will become incompressible. Density 10 to the power 17 kg per meter cube. As a result, all these layers will get a recoil, and apparently there will be an implosion, though we call it an explosion, and ultimately all the surface layers will get lifted up. And at the point of explosion, the temperature rises to such a tremendous level, starting from iron 56 to 94 in the periodic table, all the nuclei will get produced in a fraction of a second. Since in a fraction of a second, they cannot be produced in huge quantities. And on Earth, we call them rare earth elements. So my friend, instead of forget about those scribblings and all that, must be some child doing it. Sorry. It's a tremendous outpouring of energy, or on average 10 to the power 54 arcs per second. And it also tells you it is becoming one of the violent event of the universe. At the same time, the synthesis of elements. And believe me, my friend, each atom of iron in your blood, each atom of calcium in your bones, magnesium, sodium, potassium, whatever your body is made up of, atom by atom, were only created millions of years back inside a star. So, though we divide ourselves like this and that, and up and down, and black and white, and tall and short, boy or girl, we are all star children. That is the biggest connection, a physical, metaphysical, philosophical connection with the cosmos. Oh no, I've never faced this. Whatever. So I should tell you, young friends, though, if you're interested into stellar astrophysics, trying to build models of stellar evolution, it's not simple. You see that cartoon. For 3 years of your 5-year PhD, probably you have to bang your head because you're going nowhere. And maybe after 6 months of the final year, you get to your guide, supervisor tells you, okay, write down the thesis. Right. So it's tough. But we are not yet there. I have another 5-7 minutes, and I have to tell you that all the naturally occurring elements in the universe, apart from hydrogen and helium, have been produced in astrophysical scenarios. So if you want to talk about matter, if you want to talk about their formation, if you want to talk about anything, you have to look into the skies. Don't think I sell my words to earn a living. That's why I'm talking about astronomy. But in the truest sense of the term, the human mind, human psyche has realized this is the field for the future. And you see in both these cases, planetary nebula, white dwarf, supernova, and whatever is left behind supernova, I'm not going to talk about it because the next erudite speaker, very renowned researcher, she will talk about it, the neutron star and the pulsar probably. I don't know, but let us hope. Both times, there is a nucleosynthesis ending up into gas clouds, but much more synthesized than the initial gas cloud. And that tells us that the interstellar medium is not just vacuum. Huge amount of chemistry continuously going on, evolving. And that also tells us, it says, open up a new field. When we ask the question, what from we have come? Is there only life on Earth? The answer is definitely no now. We know that there should be life almost a lot of places we haven't discovered. But how did life happen to Earth? Now, progressively, scientists are trying to believe that life cannot be originated, cannot be created on Earth. Life came from outer space. Not life, not alien. Prebiotic form of life, bombarded through these initial collisions with comets and asteroids, seeded the Earth with the seeds of life. And from there, through evolution, through chemistry, through atmosphere, suddenly life sprung out. This theory goes by the name panspermia. And a new vibrant subject called astrobiology is now in vogue. Just another 3 minutes, 4 minutes, I'll say. I started at 6, around 6:45. So 5 minutes.
Go ahead, please finish it. Please.
Right. I only hope, I'm sorry for all the participants who are so eagerly in such a huge number is participating of this nuisance, I will now say by now. Whoever is doing this and thinking that he or she is becoming a hero, whatever. The last type of death of stars, very mysterious kind, still we do not understand. And initially, the stars whose masses is 25 times or more, according to the theoretical understanding, no amount of explosion of energy coming from inside will make them able to explode because the mass is tremendous, the pressure is tremendous. And ultimately, this gravitational contraction will take over and the star will become a smaller, and end up in an extremely dense region in the space, which in mathematical terms is called singularity. The density is so critical, almost infinite. It will not allow anything to go out of it and try to attract matter from the periphery. Not even photons, the light can come out of it. So in the space-time, as if there is a hole that has been created, everything is falling inside, when light cannot come out, it is dark in color, we call it the black hole. People realize that this is theoretical fancy, imagination. It's very difficult to understand, first of all, and difficult to observe. But lo and behold, with a tremendous amount of technological input and years of deep research, observational studies, scientists have realized that black holes do exist. Both. Yeah, now this Schumann is coming. Good for you, yeah. Right. So they now understand they exist, right? And you can only understand, I'm sorry, don't look at this. This is absolutely nonsense. Out of my 1,500 lectures or roughly till today, this is the first time somebody is becoming so enterprising, right? Whatever. And this thing can only be understood in the background of something called general theory of relativity, given by a very famous personality. All of you know his name, but I hardly know how many of you know his work, right? The problem with us is that we all go through, this what is idol worship. Einstein, E equal to mc squared. Even there are music on that. But what is that? I don't think a lot of people know about. Right. But his general theory of relativity told us gravity is not an attractive force, not a force at all. It is the property of the curvature of a space-time, the curvature being caused by the presence of massive bodies. More massive the body is, more is the curvature. And more is the curvature, it will dictate other bodies to come through that curvature and towards the bigger body, gravity. So using this prescription, we can now realize that we are not getting attracted at the center of the earth by a force. Rather, earth is creating a curvature in the space-time on which we are stuck. If you have to come out of that curvature, you have to have a speed of how much? Escape velocity. You all know that. And in this context, a black hole can be understood that if there is a singularity in the space-time, as if there is a tear in the fabric, the potential is deep, infinite. That probably defines black holes in a very, very nice way. And not just the point, not just the small regions of singularity, the neck. There is around the black hole, there is a region of uncertainty, unknownness. If an object, material object, crosses the invisible imaginary boundary, it will never come back. And that is called the event horizon, right? So when everybody was thinking very good, very fantastic mathematical compilations, absolute good presentation visually, stellar black holes are difficult to find. But they also realized that some of the galaxies at the very center of them, there are supermassive black holes, billion times the mass of sun. And these galaxies are called active galactic nuclei. One of them was M87, right? And they've realized that as matter is going round and crossing the level of the event horizon, because of the tremendous speed and friction, huge amount of X-ray will be produced from the disk. And the disk will be very visible, called the accretion disk, because it is accreting matter. And in the perpendicular direction along the magnetic axis, very high powered, very fast moving ionic charged particles will flow around, creating a torchlight, a searchlight effect. So if you can see the structure of an accretion disk, you know black holes are there. And lo and behold, these are all simulations by NASA and how a stellar black hole will look. The inner circle is almost dark because of the event horizon phenomena. But a couple of years back, this is not the picture they got. This is from the movie Interstellar, but the similar picture they got. The first time, the shadow of darkness. An object you are seeing which does not emit light. Just by the effect of the object in its surrounding, seeing the accretion disk. You see the round you are seeing, the upper side of the round is something called gravitationally lensed image of the disk. So black holes are there. So my friend, at the end of this period of 1 hour continuous lecture and 1 hour continuous scribbling, we have to say that all these objects that you see, the stellar things, contents, is part of a huge system, 20,000 crore stars, from one end to the other, 1 lakh light years, 100,000 light years, called Milky Way, with 5 to 6 prominent spiral arms spinning, Earth going round the center at a speed of 220 kilometers per second. Amazing. And the whole galaxy is moving in a particular direction, 365 kilometers per second. So in this 1 hour, we have realized that because of the advent of technology, because of the progress of human mind in deeper and deeper mysteries of nature, the universe has opened up. And through our mind, through our eyes, through our telescope, we are realizing that though sometimes we boast that we know a lot, like this student here who is trying to say that he knows a lot about lot, but we hardly know anything. And that is the biggest plus point, because human mind always tries to go into the unknown. Something has to challenge the human mind, and the universe is challenging the human mind in the ultimate sense. Thank you very much.
Thank you very much, because I think it was a very scintillating talk, and all the participants have absolutely enjoyed it, notwithstanding this one person who's decided to be an annoyance. There are multiple comments saying that despite the scribbling, they were really enjoying. So I have already collected more than 35 questions, so I think Yes, that tells you how much they were enjoying.
Thank
But without much further ado, let me invite the next speaker so that we can hear her first. Thank you very much again, and we'll come back to you with all our questions that we have kept here. Thank you. Our next speaker is Dr. Pragati Pradhan. We have been informed, she's currently at the MIT Kavli Institute for Astrophysics and Space Research. She did her BSc from St. Joseph's College, Darjeeling, and MSc and PhD from University of North Bengal, along with Raman Research Institute, with a postdoc from Penn State University. She's extensively studied data analysis from X-ray satellites like Suzaku, XMM, Chandra, NewStar, etc. And her research interests mostly revolve around timing and spectral analysis of isolated and binary neutron stars and their transient behavior. For her postdoctoral work at MIT, she's focusing on stellar wind diagnostics of OV stars and cool stars with the help of high-resolution spectral Chandra HETG. Today, she'll be speaking about space navigation with X-ray pulses. I think this is a topic that's pretty exciting to all of us, and we are looking forward to your talk, Dr.
Thank you. Okay.
Before we start, I hope you have been made a co-host, and then you can actually disable everybody else's annotations so that we don't face the same problem again. Can I request the host to make Dr. Pragati a co-host? And then disable everybody else. Yes, that's good. And now kindly disable any participant from interacting. Only the hosts can allow, and then she'll be in full control. Yeah, I think we can start off.
Sure. Thank you, Madhurima ma'am, for that excellent introduction. I would also like to thank Dr. Samir Bal, principal of Pershing College, for hosting such events, along with the convener, Dr. Amit Sankar. And clearly, Dr. Dipi Dori, his talks are always has been a great pleasure to listen to. I had the good opportunity to listen to him when I was attending an orientation at North Bengal University, and he's one of those people who has really inspired us to follow the field of astrophysics. So I'm really glad to share the stage with him. So today I'm going to talk about space navigation with X-ray pulsars. And since I know that the audience is very diverse, what I'm planning to do is what I have actually, the way I have constructed this lecture is in such a fashion that the first, a large portion of the talks can be followed by probably everyone there at an introductory level. But towards the end of the talk, things can get a little technical, and I intentionally did that just to give a sneak peek into what we do as astrophysicists. And if there are portions of the slides that you're not able to follow, I'm happy to take questions, or you can also email me towards the end of the talk, and I'll either try to answer your questions or provide you references or connect you to somebody who can really answer these questions. So let's start. Like Professor Dori already mentioned, astronomy and navigation go way back in time. Humans were clever enough to identify one star on the celestial sphere, which was unchanging, and following that star, you could really locate your position on in space. So basically, the whole idea was something like this. If you look into the North Star, and then you can kind of angle yourself to the North Star, the angle that the horizon makes with the North Star, as you can see in this picture, this will give you the latitude of that place. And this was especially relevant when a long time back, when human sailors were for long voyages in the sea where you could not see land for many days. There's one thing that you could follow, and that was the North Star or the celestial sky. Of course, these days we don't have to do that, and we have something called the global positioning system, which is the device which is embedded in most of our smartphones. And the principle for global positioning system is really that you have a lot of satellites which are orbiting around this Earth, and at any point your mobile is able to, or your GPS receiver is able to get signals from at least four receivers. So the reason behind this is when we use information combined together from these four receivers, you are able to locate, we are able to, the GPS system is able to locate your location as well as the exact location on the surface of this earth. And I'll go into this a bit further. So basically, if you are on somewhere on the earth, you can locate, your location can be identified by using a combination of these four satellites. And let's look into this a little further. This whole method of really finding your position with respect to on earth is through a principle called trilateration. And because of course we live in a 3D world, and we would rather talk about spheres instead of circles, but for the sake of a simple understanding, I'll first start with this principle of trilateration for 2D. That means just imagine the world in 2D, and let's say you are at this point anywhere on earth. For simplicity, consider the surface of this earth, and then you have two signals coming from two different satellites to your receiver. So what you do is, the principle behind this is you just calculate the distance that you are from the receiver by simply noting the time at which you receive the signal and the time at which the signal was sent. So if this is T2 and this is T1, T2 minus T1 into the speed of this light is basically the distance that you are from this receiver. And similarly for this case. So that is how you determine the distances between these two satellites. For example, if R1 is the distance here and R2 is the distance here, consider, you can, like for example, if you consider one of the satellites, and you can be anywhere here around the circle represented by this satellite. Similarly, for the second satellite, you can be anywhere into this circle. So you realize that you will be at that place where both these conditions are fulfilled, which means that you can either be here, or two circles intersect at two different points. So you can either be here or here. But considering the fact that you should be closer to the sphere of Earth, what you do is you consider this Earth as the third sphere. So that's how you locate your position. Oops, sorry. Maybe I can speed it further. So considering this Earth as a third sphere, what you can do is you can identify yourself at this position. So now what you do for 3D is something very similar, but instead of these circles, think of them as spheres, which is the case in real world. So in case of 3D, you have let's say three different satellites, and you want to find your position on this Earth. What you do is, the principle is the same. You draw a sphere around yourself with the radius as the distance between you and the satellite. Uh, and once you do that, you see that when two spheres connect, they connect along any line on a circle like this. So what you do is you need a third sphere to really connect this. So what you do is you combine a sphere with a circle, and then you can find two common points here. Now, as earlier, what you do is you use the surface of this Earth as one more constraint and fix your position at this point. So this will be your position on Earth. Now, one thing I didn't mention here is we can use three different satellites to identify your location on Earth. But you realize that because we are working with GPS of receivers on our phones, the clock precision for the error in determining the time for the mobile phones are much larger than, let's say, for satellites where they use atomic clocks. So because a little amount of error, realize that when you remember that you are multiplying it by the speed of light, so that can give you errors in orders of kilometer. So what you do is you for in real life you use a fourth sphere, so that we can identify exactly where you are on this Earth. So this is basically the principle of trilateration that is used in GPS. Now, the reason I'm mentioning this is later on when I talk about X-ray navigation, we will use the same principle in order to determine our space, our location in space, but that is for later. Um, of course, and then I come to my favorite topic. We know that humans have been using astronomy for a very long time for navigation, but it is fascinating to know that there are a lot of animals as well which use astronomy in their everyday life. Now, today I'm not going to talk about them in details. I know a few of people who've attended my previous talk know that I spend a lot of time just thinking about them. So these are indigo buntings. These are those birds that actually can identify the north and the south direction, and using the magnetic field of this earth, you can use. So what they do is when they have to navigate very long distances, they can use this information. The next is these are harbor seals. So the experiment was conducted on these two seals in an enclosed planetarium, and what was identified was that if you sufficiently reward the seals, they could identify Sirius as the brightest star in the planetarium. So this was just a proof of concept showing that seals can really also look into the night sky and identify stars. And then you have the jumping spiders. Now, the reason I saw the jumping spiders is because their eyes are very similar to Galilean telescopes, which means that they have an eyepiece and a refractive. So what you do is you can really focus onto any object similar to how a Galilean telescope would. And also they use the principle of chromatic aberration, which means that light basically behaves, you focus at different points depending on what color wavelength of light that you're using. And because they use this principle, you can also this is a very relevant technique called depth perception that can be used for automating image processing in astronomy. But today I'm not going to be talking about any of them. These were just teasers to guide you and probably just make your mind a little curious so that you can go and read about them. But definitely I'm going to talk about a couple of slides, 2 or 3 slides about these fascinating objects. Now, these are the dung beetles. Dung beetles are these are tiny creatures which are found mostly in deserts, and they have very simple life goals. So what they do is they collect dung for dinner, which is their food, and then they make these balls of dung. Basically, they make a poop ball, and then they transport this ball from where they have collected to their home, wherever they live, for their families and children. So what they do is that, and the way they do it is very fascinating. The dung beetles actually don't really walk like we do, switching on navigation, but they follow the path to the home using something called the Milky Way galaxy. I'll explain why they don't use stars and Milky Way and instead use Milky Way galaxy. Um, but what they do is they basically, and they don't move like forward, and they don't move forward, and probably because their hind legs are stronger, or because they've just learned how to walk that way, they climb onto the top of the dung ball, and then they have their hands rested on the ground, and then they push the ball of poop backwards with their hind legs. I'll show you a video of how this is done. And the reason why they use Milky Way and not celestial stars like we would is because their eyes are not built like ours. So this is how dung beetles would see. For example, they have compound eyes, and they see every object as in tiles. They cannot resolve it. And this is how we see it. We see this as a big picture, and we combine all the images together to form a smooth image. And the limitation of having this compound eyes is that you can't really see a star. For example, this is a snapshot of Milky Way as would be seen by dung beetles. You see that there's supposed to be a star here which would appear to a human eye, but because you're simulating this based on how dung beetles would see it, you don't really see this star here. Instead, what you can really see is this band of Milky Way. So what these dung beetles do is they take a snapshot, and then they realize, oh, this is the direction I should be going, and then they follow that way. And this is an obligatory video for how dung beetles do their dance. So they climb onto the top of the dung ball. This is when they are probably looking into the celestial sphere. remembering how Milky Way looks like, and this is how they go back to their home. Now, this is very fascinating. If Milky Way is being used by animals or creatures on Earth to really navigate their way across the surface, so we humans should definitely think a little more forward than that. So here is where my concept comes into being. So what I'm going to talk about next is I'm going to talk about something called autonomous GPS. Now, henceforth, whenever I say GPS, I don't mean the global positioning system. Instead, what I mean is the galactic positioning system. So the whole principle behind this is something like this. Right now, what we do is whenever we have any spacecraft go into space, uh, we communicate to them on Earth. You have these control stations on Earth. So what you do is you communicate with constantly through radio frequency with the satellite, and then you can locate where exactly it is, where it is moving, and so on. Now, while that is sufficient and so far has been doing a great job, tremendous job, of course, but what if we could improve the technology in such a fashion that instead of communicating, and I'm talking about spacecrafts that go out in the space, like Voyager, for example, or any X-ray spacecraft that goes further into interplanetary space, that means within planets. Instead of using the technique that we have right now, that is constant communication with Earth, what if we could use something else that is already there in space and that can actually be used for navigating across, just as I showed the diagram of three different satellites that can be used in order to locate your position on Earth. Similarly, we can do that by using three different pulsars. And Professor Dowry was right when he said that I'll definitely be talking about neutron stars, or AKA pulsars. So this is the video of a pulsar. I'll just show you what it is superficially, and then I'll explain how this is formed. So basically, pulsars are made up of neutron stars, and they are rotating on different speeds. And what we do is, because most of the pulsars, when they are formed, their magnetic axis is not aligned to their rotation axis. Every time it rotates, we see flash of radiation. So pulsars are also called called the lighthouse of the galaxy. For example, this is how a pulsar would appear. So these are the magnetic field lines, and the magnetic axis and the rotation axis is not co-aligned. So let's say if you are observing from far, the effect is that we would see them as lighthouses or pulses of different frequencies. And I'm specifically talking about those emission. Now, pulses can emit in a lot of wavelengths. It can emit in radio, gamma rays, or even or X-rays, or even lower. But today I'm just going to be talking about X-ray pulsar navigation for a lot of reasons, and one of them being that they are quite well understood. They're very bright, and again, like Professor Dori already mentioned, we can talk about wavelengths, we can talk about optical or radio wavelengths on Earth, but X-rays cannot pass through the Earth's atmosphere. So in order to observe X-rays, we have to send an X-ray satellite to space, which means that when we are observing X-ray pulsars, there is no interfering medium in between, and that doesn't diminish the strength of the signal in X-rays, unlike a radio or other wavelength when you are observing from Earth. So this is one major reason why X-ray pulsar navigation is a developing field and is an essential field for when we want to talk about autonomous galactic positioning system in near future. Now, I'll just show you a quick video of how the neutron stars are formed. You realize that they are very dense. Neutron stars are very dense. You could almost fit 50 million elephants in 1/3 of the size of your finger. And the way they are formed is, this was also touched upon by Dowry sir. Somewhere in the universe, the one of the stars, they just run out of fuel. And what do I mean when I say fuel is something like this? So whenever there is an accumulation of a lot of gas, what happens is at the core of the star, all the hydrogen starts to combine to fuse into helium, and then helium combines to form heavier elements. And when this is happening, you have a lot of pressure which is being radiated in the outward direction, which is the radiation pressure. And at the same time, because of the mass, you have gravity which is acting on this ball of a star, which is pushing in the inward direction. So a stability basically comprises of an equilibrium between the outward force and the inner force. When the stability is lost is when things start to happen. And stability is lost when, let's say, when the innermost region of this circle, of this sphere, forms something called iron. You know about iron, of course. You can't fuse this into heavier elements and release energy. Basically, it is not an exothermic reaction. So what happens is the star runs out of fuel. So the gravity crushes it inside because you have no supporting pressure, and something like a supernova happens. Basically, the star explodes. And what is left behind, and you have a lot of gaseous emission, heavy elements which are being transported across the universe, and what is left behind is this ball which now starts spinning because it has received a lot of rotational momentum from the explosion. And here you see it forms a very small dense matter. And here inside this, these are mostly formed out of neutrons, but they are squeezed in such a small space that atoms no longer exist. Instead, what happens is the neutrons start to become degenerate. That is, you use there's a surplus of more neutrons inside this, and what is formed is a neutron star. And because of the kick it receives during supernova explosion, it starts to rotate at different frequencies. Um, so looking at the pulses from these pulsars, we can identify what pulsar we are actually looking at. Basically, pulse profiles or the pulsation characteristic for each of these pulsar can be used as a fingerprint, which is very unique for each pulsar, because you realize that in order to get X-rays, or in order to get radiation, it is a lot dependent on the geometry and a lot of other factors and how it was created at birth. So basically, it suffices to know that pulse profiles can be used as pulses fingerprints, and that is the premise for building up X-ray navigation. So for example, this is just a simulation to show how pulse profiles are seen by us. Note that every time the pulsar is rotating towards us, you see a peak here in X-rays. Now it is the information of these pulse profiles that we will be using to explore X-ray navigation using pulsars only. Now I just want to give a recap of what we have already done so far. Um, in the form of a video. Now we are talking about a global positioning system, or on space, that is the galactic positioning system. And in order to do that, we use something called pulsars. And the reason why we use pulsars is because their magnetic field and their rotation axes are misaligned, causing beam of radiation to pass through us at a constant frequency. And when we collect signals from these two pulsars, one pulse profile for one pulsar is very different from pulse profile for a second pulsar, and this is the prerequisite for carrying out X-ray navigation techniques. Now, the next thing is, how do we go about doing it? Now, what I'm going to do is I'll try to explain the how using this diagram here, and in the next video, I'm going to reiterate the same but with a video. Now, let us first concentrate on number one. Of course, here we'll start with this point. What this typically means is that in order to in order to know your position, that means in order to know the position of the satellite in space, one thing that has to be done is we have to just assume the last known position. So let's say you know that the spacecraft was somewhere in space. So you collect that position and you do your calculations. How I'll talk about this one by one. And then you do your calculations, and in the end you make a check. And then you make a check and see if your initial assumption here was correct or not. Now, if it is correct, then you have determined your position and velocity accurately. But if it is not correct, then you go through the same process iteratively till you obtain a position, the right answer in this case. So in order to do that, what we do is we just assume a position or velocity for for the spacecraft. And the next thing to do is to switch on the spacecraft. Basically means to you don't really switch it on physically. It means that you are actually pointing the spacecraft towards a pulsar, and then you start counting photons received from that pulsar. When I say photons, I simply mean X-ray radiation. So you are collecting X-ray photons from the pulsar at constant rates. So you have the photons, you have the time at which it arrives, or the time arrival of the photons. Next, what you do is you do something called barycenter correction. Now, this essentially, it may be a technical term. Basically, what this means is we astronomers, all of us agree to use one frame of reference. Otherwise, it can get very confusing when you are talking about time if you don't know what frame of reference you're talking about. So we all have agreed to use the one frame of reference, and whatever time that you receive is now shifted to that frame of reference, or what we say is we make corrections to get the correct time, so that when I talk to another astronomer, he or she knows that I'm talking about barycenter corrected times. So once you receive the times from this pulsar, you make barycenter correction to it, and then you create pulse profiles out of it. Basically, the way to create pulse profiles is you have a lot of pulsations, you fold them together at the period of this pulsar, and that will give you a nice pulse profile. Now, one thing that we should, when I mentioned that one of the prerequisites for the X-ray navigation is pulse profiles from pulsars. What can be done is before the spacecraft is loaded, launched from Earth, you can fill the satellites with, you can fill the X-ray spacecraft with templates of perfect pulse profiles that can be seen from different pulsars. And what you can do is the next step is basically the measurement or the comparison between the pulse profiles that we obtain on the satellite, that is the measured pulse profile, and the pulse profile that is perfect, or the template of this pulse profile. So once we make a comparison between them, which is called the time of arrival measurement, we can make this a measurement, basically compare your data to your model, and then you check if there is a phase shift. Now, if there is a phase shift, then this simply means that your position or velocity that you assumed earlier is not really correct. So what you do is you just go through this whole process again, maybe a couple of times, till you reach at this point where there is no phase shift between them. That is the pulse profiles are perfectly aligned, which means that the position that you obtain is really the position of the satellite. So this is basically the principle between about how X-ray navigation can be carried out. I'm going to say the same thing now, but in video form. Now, like I mentioned earlier, one prerequisite is you just load the X-ray spacecraft with a couple of different pulse profiles. For example, before it is launched from Earth, what you can do is you can study a lot of, you have a database of pulse profiles. You can study a lot of pulse profiles. You have a database for them. You load them to the X-ray spacecraft. And the next step will be, once this is launched, the next step will be to really find this point here. That means the last known position of the satellite. So once you know the last known position, the next step will be to really collect photons. Basically, this satellite is now pointing at different pulsars in order to generate, in order to create pulse profiles. So then the next step here is to really perform barycentric correction. You don't really send the pulses down to ground, but this depiction simply means that you can make some barycentric correction. I'm sorry, this. So when you make this barycentric correction, the next step will be to really generate pulse profiles. So what you do is you fold the photons according to the spin value, and you obtain the pulse profiles. So let us look at this again. So when we know the last known position, we start the observation, that is looking into the pulse profiles, and then you shift this to some barycenter, that is make some barycentric corrections, and finally generate some pulse profiles. Measure this to a template and check if there is a phase shift. For example, there is no phase shift, so this is good. But if there is a phase shift, for example, you see it here, then you make this correction again till you arrive at a particular correct position of the satellite. Now, here I come to what I was talking about, the principle of trilateration. Remember that when you are just looking at one pulsar, you can be anywhere on anywhere at any point where this where which is satisfied by a single point, basically. So it's this the observation of a single pulsar is not really meaningful. So what you do is you measure a couple of pulsars, and like I mentioned, using the same principle, you need at least three different pulsars in order to identify where in space you are. And once you identify that, you'll be able to and that's the goal, that's the basic goal of X-ray navigation. And X-ray navigation, although it has been it's a new thing now in terms of technology, the the idea, the conceiving of this idea had happened a long time back. And here I show a golden record, the golden record which was placed in Voyager by Carl Sagan and his team. Basically, you have all the information about Earth here, and at a certain portion you also have information about, this is
Pradhan,
called the pulsar map. Yes.
another 5 minutes or so.
Okay, I'm almost done. Sure. Thank you. Mhm. So you have something called the pulsar map here. So basically what it does is you can, depending on this position, how the length of this line, you can identify where exactly Earth is with respect to the huge space. So this is really a good time to invest in X-ray astronomy and X-ray navigation in space. And clearly, there was a demonstration in 2018 by a group of scientists at NICER, where they used a couple of millisecond pulsars to really identify where in space they were. So this was an excellent proof of concept, I would say. But there are, of course, a couple of limitations or challenges. I'm not going to talk about this in detail, but the challenge behind the two very generic challenges are: firstly, the pulsars lose energy, so their rotation speed will change over time. And secondly, sometimes, because the neutron star is made up of fluids and superconducting matter, there is a slight readjustment of matter, and that causes glitches. So that can cause some disruption in the pulse profiles. But to correct this, it is pretty simple. What you do is, in this case, you can just recatalog. That means, like, you have the most recent measurements, and then you feed it to the spacecraft, and here you can just write an efficient, clever algorithm to just do away with non-repeating parts. So this is what has been can be done in future, and we have done similar kind of work. For example, this was for a pulse profile for one pulsar 1509-58, and what we did was we just looked into the stability of this pulse profile. So, and one way to do that, as you know, is to decompose this the pulse profile into Fourier components and measure their amplitudes and phases. So once you do that, you can really justify whether or not the pulse profile is stable. And this is just some simulation that we did. So the x-axis is the number of photons here. What you do is you can see, so this is the measurement, or the time of arrival measurement that I was talking about. Basically, what this just means is that the more agreement here, that means if it is a constant value almost here, means that you are making more accurate measurements. And you see that for larger number of photons, 10 to the power 4 photons, which may seem like a lot, but it is not for a bright pulsar. For 10 to the power 4 photons, you can really accurately estimate the position of this pulsar. And with some back calculations, we found that around 450 kilometers can be achieved in nearly 15 minutes of observation. Of course, there are different better pulsars, better as in pulsars that are rotating very fast with stable pulse periods. And one active field of research is to identify these pulsars that can be used for X-ray navigation. So I think that time is right now very ripe, as in you have the legacy for the X-ray navigation already established, as well as you have a proof of concept here. So the next step definitely is to test this further. And indeed, if you look at this article here, this came up a couple of months back, you see that NASA is really planning to use X-ray navigation in an upcoming mission to the moon, which we call Artemis. So I would say this is a very active field, and I would request you to stay tuned about this. I personally, because I work on pulsars, I'm very excited about this. And I'm happy to take questions. I end my talk here. And these are the references in case you want some further reading. Thank you.
Sorry, I got disconnected. Um, yeah, I'm sorry, I got disconnected, so I just missed the last part of what Dr. Pradhan was saying. It was navigation using X-rays is something that we are not really used to listening about. See, I have a collection of over 50 questions for both of you. So that's the reason I'm hesitating a bit, because I don't know where to be starting with this. So maybe a couple of questions to both of you. But before that, I have a small comment to make to the participants with the permission of the principal and others. See, the thing is, with online education, the responsibility of learning falls with the student, because you're sitting behind the laptop. You could be opening 5 different tabs and doing what you want to do, which means you have to be behaving in a much more responsible manner than scribbling on the screen and asking for feedback form all the time. This is disheartening, because when people are taking so much of an effort to give such beautiful, presentations and really tell you, um, I think you have to get more responsible. The old way of saying that the teacher is responsible, I'm going to behave like a school student, is not going to work anymore, especially with online education. I'm sorry, but I had to say this because this was really, distracting most of the participants who were very keen on listening to both of you. So thank you both, the speakers, for an excellent talk, both of you. And like I said, I have 50 questions and I don't think I have the time to be. So I'll alternate between Dr. Duari and Dr. Pradhan. Um, One question, Dr. Duari, is how do we know what is in the interior of the sun?
Okay. As I mentioned earlier also, no probes, no physical probe can go inside the sun because of the tremendous temperature. So basically, trying to look into the different properties from the Earth or from the surface through scientific theories and understanding, we try to build a model. We can try to understand what is not at inside, but what just below the surface, how is it, by a process called helioseismology, which is like earthquake, sunquake. Because sunquake happens because of sound waves propagating from inside to the surface and some getting reflected back. There is a pulsation on the surface. And to measure the Doppler shifts of these pulsation and trying to come out with the different frequencies of the pulsation, from there, trying to understand whatever there is inside from the surface, not at the center. And then using all these data, as I mentioned, using the equation of hydrostatic equilibrium, mass conservation, energy transportation, and energy production, you put it in a computer, because you cannot solve it through pen and paper because of the very critical boundary conditions, very steep sort of gradient, and as a result, you get a model. That's how we get it.
Okay. Thank you for that reply. Dr. Pradhan, one question to you is that given that the dung beetles seem to be relying on the Milky Way for their navigation, what happens when it's cloudy, and how does light pollution affect them? And there was a philosophical question add on to that, saying, if their sense of reality is different from our reality, is there an absolute reality?
I'll try to answer that. So to the first question, indeed, when we talk about dung beetles, there has been this is the question that I get almost all the time, and that is what happens to let's say dung beetles on a cloudy night, for example. So there has been experiments going on in enclosed spaces, and definitely on a cloudy day, dung beetles would just take a little more time to reach their place. So they would have their some amount of cognitive memory among themselves, and either they use that, or they just fumble about and find their way and finally reach the place. It is something like having heavy traffic and that it takes a lot of you navigate across, but finally find your way. So that's basically the answer that we have right now. And I don't believe in absolute reality, so I think that is
About
absolute.
light pollution? Light
Yes,
pollution
light
would be the
pollution
same as.
is a huge factor. Yes, light pollution is a huge factor, and the only explanation that we have right now is because dung beetles are found in deserts which are very remote. So that has not been affecting them as directly as it has been affecting, for example, like the sea, which is located close to a city, for example. But definitely there has been studies about light pollution and how it affects animals in general, including dung beetles as well.
Okay. Dr. Gauri, a question for you, please.
Yeah.
I'm trying to keep the questions at a general level. There are very technical ones, which maybe over the email the organizers will share with you. How does one become an astronaut? How does one work for NASA? And what is the future scope of becoming an astronomer or sending people as astronomers from India?
See, first of all, astronomy and astronautics, these are two separate things, right? Astronomy is something which you talk about stars, galaxies, the environment in a cosmic sense, either through observations or through your research, theoretical research. For astronaut or astronautics, you have to know a lot of technical knowledge, right? It is not only just astronomy, astrophysics, because basically you have to have an engineering degree, and on relevant engineering degree, not say civil engineering or something like that, but which is related to astronautics, and also aerodynamics, aeronautical engineering. Generally, these people, they know much better how to manipulate or how to use a spacecraft. Because astronaut means you have to go somewhere in space in a spacecraft, and you have to control that. Astronomy, you can just sit in front of your laptop if you want and do a lot of astronomy. So, but the basic degree should be probably, preferably physics or mathematics, because that makes it easy. But in India also, if you have an engineering degree, say mechanical, electrical, electronics, computer science, metallurgy, even then you can join astrophysics or astronomy research. Because the topmost, there are some 18, 19 institutes in India. They have this joint program called JEST. It's a screening test, which you can
Right.
apply to. And if you're good enough, by the way, you have to be good enough. Otherwise, deciphering from the signal of light what is happening up there is difficult. So anyone can be an astronomer, and in India, it is thriving. Believe me, scene is very exciting. New things are happening. New telescope are being planned. Plethora of collaborations with top-notch universities and institutes in the world, even with NASA. And let me tell you one thing. Becoming an Indian astronomer in one of the institutes is as good as becoming a NASA scientist. Right.
Exactly. Yeah.
ISRO scientists are doing some places much better than NASA scientists. You have to take all the dynamics, the budget, the number of people, the pool of talents from throughout the world coming into NASA. So all these also play a factor. But what a satisfying feeling if being an Indian, to stay in an Indian institute, obviously learn from outside, learn from the best, but do your productive work. Stay the productive year in India, because India is happening.
Thank you so much. I mean, that's really true, because I think this is one place where India is doing very well, and we have to be proud of ourselves. I think I'll kind of ask the last set of questions, because we are maybe closing. Dr. Pradhan, repeated question is, how are pulsars formed and how are they different from quasars?
So basically, pulsars and quasars are very different in a lot of ways. But let's think of this as pulsars are very small, compact objects, which I showed it. There's a big star, and it super explodes, and then you have a remnant. It's basically a very small, compact object. But when you're talking about quasars, quasars are basically very huge, extended galaxies, at the center of which you have a supermassive black hole. That means very large black hole, billions of solar masses. So these are positionally in spatial extent, they're very different. One is small, the other is very large. And also quasars don't have like, because pulsars, they have this magnetic field and the rotation axis misaligned. You don't really see quasars which are rotating at all, if and definitely not at a constant frequency. So they're very different. Definitely both of them emit in X-rays, and they're very interesting objects to see it, but they are very two different. We are talking about very two different things.
Thank you for that. And I think I'm going to pose the last question because we are really running short of time. There were a series of questions to Dr. Dwari about the flipping of the magnetic poles, both of the sun and of the earth, and how they impact each other. So, in brief.
Yeah, flipping of the magnetic poles of the sun, it happens quite regularly, almost 11 years, every 11 years, which is called the solar cycle, right? And I think most of us are aged more than 11 years. And in our lifetime, there has been quite a number of flips. Nothing big has happened. So obviously, some changes of the sun and its characteristics and behavior and magnetic pattern and all that, including the sunspots in the northern hemisphere, if they are north-south polarity, in the southern there will be south-north polarity. These things are there. But apart from that, there is no big change. But for Earth, you read in the social media, every 55,000 years on an average, the magnetic field will flip. That can cause a problem. The smallest problem that we will face is that whatever used to call our north pole of a small magnetic compass that we have our home, it will try to do the opposite now. But we have to adjust in our brain that, okay, now this is north, this is south, and what is geographical north and geographical south. That is one. But the communication system, the satellite system, the GPS communication positioning system, everywhere there has to go to be a reorientation, because all of us, all these instruments, they use the magnetic field of the Earth, including landing of a plane when you're putting it on autopilot, right? So everything should go through a phase shift, I will say, or a reorientation if the Earth's magnetic field changes, right? Sun's magnetic field, in a very direct way, I think nothing happens. No wrong thing happens. But Earth, yes, it can happen.
Thank you. I think in summary, I can only read out the last comment which has come, which says, what a session, so informative and very easy to grasp. And I think that really summarizes both our speakers, Dr. Gauri and Dr. Pradhan, and the enthusiasm, sheer enthusiasm that both of you have brought to this talk. Like I said, there are 50 questions. I'm feeling very bad about not being able to pose them, but it's physically impossible to be continuing this. I would request the organizers to kindly communicate with you. Maybe you can answer them over email and write back to the participants. Thank you very much.
And thank you, Professor Majrima, for doing a fantastic job. Thank you so much. Thank you.
Good to see you again. Thank you.
Good to see you. Yeah, bye. Back to you, Amit.
Thank you, Madhurima ma'am, for nicely coordinating the sessions and putting all the efforts to combine all the questions and keeping with the speakers. And I would like to thank our speakers, Dr. Dwari and Dr. Pragati Pada and Pragati Didi, for such a wonderful session that you have given to all the participants. And at the meantime, it's our sincere apology from our organizers that we could not control such kind of activities that some of the participants were doing, all the paintings and all, especially to the Dr. Dwari's sessions. So we are very sorry for that. And all the participants also, we tried our best to control that. However, we could not control it, maybe because of our lack of some expertise in all, and we are also working on it. And we have learned a lot of lessons today, the today's session, and we believe that in the next sessions it will not be repeated, and we will follow whatever things has been instructed today. So okay, so with this we are at the end of this session, and for that I would like to request our the co-convener of this session, Dr. Himanshu Joshi, to kindly deliver the vote of thanks from on the behalf of the organizers. Dr. Joshi, please.
Thank you, Dr. Amit. I hope I am audible.
Yeah.
So, a very
Yeah.
warm good evening to the speakers, eminent professors, scientists, participants, and everyone present out here today. It's an honor to have been asked to offer a vote of thanks on the occasion. So I, on behalf of my colleagues and the entire organizing committee, express my hearty vote of thanks to all the speakers and participants for gracing your important work and sharing with us your findings and opinions today. First of all, a very big and sincere thanks to the patron, Dr. Samir Ball, Principal Caution College, Darjeeling, for his encouragement towards organizing such an event and also for his continuous support and guidance throughout. Thank you, sir. I may like to express our sincere thanks to Dr. Devi Prasad Dwari, Director, Research and Academics, MP Birla Institute of Fundamental Research, MP Birla Planetarium, Kolkata, for an excellent coverage to the topic, Challenges in Astronomy and Astrophysics. Thank you, sir, for all the initiative that you took for this event. And I believe that all the young minds present here would definitely have been inspired by your great words. My sincere thanks to the speaker, Dr. Pragati Pradhan, MIT Kavli Institute for Astrophysics and Space Research, USA, for her beautiful explanation on the topic space navigation with X-ray pulsars. The topic itself being quite attractive, I could definitely say that the young researchers got a take-home message from the inspiring and interesting talk. I would also like to share that Dr. Pradhan was my teacher during my BSc course, and I was fortunate enough to be one of her students. Thank you, ma'am, for your presence today, and also for everything that you have taught us. I must mention our deep sense of appreciation to Professor V. Madhurima, Central Department of Tamil Nadu, for coordinating this event to a success. Professor Madhurima has coordinated various events with us in the past as well. Thank you, ma'am, for your continuous support and for always being there for us. You have always managed to be together with us in all events, and despite of your very busy schedule and your active involvement in various research activities. So on behalf of the entire organizing committee, please accept our sincere gratitude and a humble thank you. Finally, I would like to take this opportunity to place on record our hearty thanks to the entire participants. Thank you all for your cooperation and your active involvement, without which the event would not have been possible. Also, I extend my sincere thanks to all the technical committee members, Mr. Mahesh Ram, Mr. Nihal Limbu, Mr. Manubindu Das, and Mr. B.K. Rai for taking care of all the technical issues. I also thank all the faculties and all the non-teaching staff of Caution College for their continuous support. My apologies if I have missed any of the names. So therefore, I thank everyone involved and their willingness to take on the completion of the tasks beyond the comfort zone. Once again, I want to state that we are most grateful to all the speakers and our coordinators, and we thank you for being with us this evening. It has been a great pleasure. Thank you very much. Okay, over to Dr. Amit.
Thank you, Dr. Joshi, putting such an effort to deliver the vote of thanks from the chair of the co-convener of this organizes Caution College. And I would like to once again thank you our speakers and the coordinator of the session, Dr. D.P. Dwari, Dr. Pragati Pradhan, and Madhurima ma'am once again. And I would like to apologize to the participants as well as the speakers for such a activities from the participants that we could not control it once again. So with this, we have already provided the feedback links to the participants in the Zoom platform chat box as well as in the YouTube sessions also. So you can give your valuable feedbacks, even though we know that what ahead. So we request you to provide the feedbacks, and the certificates will be provided to you from tomorrow onwards. We are working on it. And with this, I would like to thank all the participants and my organizing team members and the speakers. So with the approval of our principal, the patron of Coaching College, Dr. Samirabal, we would like to end the session here and conclude this event. Thank you very much. We're concluding it. Stay home, stay safe. Good night, everyone.